In this video, we'll be discussing the difference between a planet's observed and effective temperature. In addition, we'll be going through a brief evolution of Earth's atmosphere. To begin with, we can reason, of course, that the number one contributor to a planet's temperature is the sun and its solar output. And we can reason that any planet that is really close to the sun would be much likely a higher temperature than a planet that's further away from the sun. And we have a law for that. That law is called the inverse square law. And an example of its use is in the equation over my head. But to begin, let's look at the diagram representing it graphically. What you see on this x-axis here are numbers 0 through 5. And what those numbers represent is d in our equation, the distance between the planet and the sun. And you're probably thinking, wow, those are really nice numbers. They're really easy. It's because we made them that way. We defined them that way. So 1 astronomical unit, by definition, is the average distance between Earth and the sun, which is about 93 million miles. So that is what we define as 1 astronomical unit. So if you look at the bar, the blue bar next to Earth, that goes up to 1 on the x-axis. The y-axis gives the planets' names. If you look at Jupiter, it's over 5 astronomical units away. So it's at a greater distance from the sun than Earth is. If we look at Venus, it's at about 0.72 astronomical units away. So the bar is about 3/4 of the way to 1. All right. So looking again at our equation, S represents the solar flux density at the top of the atmosphere for any planet in our solar system. And we can determine it just from knowing the solar flux density at the top of Earth's atmosphere, which right now is about 1360 watts per meter squared. And this varies, and we'll discuss how and why this varies a little later in the course when we get into orbital scale impacts on climate. But for right now, it's about 1360 watts per meter squared. So then if you look at D represents the Sun-Earth distance. The D subscript Earth is for Earth, so that would be 1 astronomical unit. Say we want to calculate the solar flux density at the top of Venus's atmosphere. So that would be our S on the left-hand side of the equation. Well, for D, the D that's below D sub Earth in the equation, we could sub in 0.72 astronomical units. So we could determine the solar flux density at the top of Venus's atmosphere by taking 1360 watts per meter squared, which is the solar flux density at the top of Earth's atmosphere, times 1 astronomical unit divided by 0.72 astronomical units. We square it, and that will give us a solar flux density at the top of Venus's atmosphere that's about twice that of Earth, so about 2,600 watts per meter squared, which is exactly what we'd expect. We would expect it to be warmer at the top of Venus's atmosphere. But the thing is, when we go and we look at the temperature of Venus, what the temperature of Venus would be if it didn't have an atmosphere, it's actually kind of low. So let's discuss this a little bit. So Venus is, like we said before, 0.72 astronomical units from the sun. So closer than Earth is. However, because of different features of its surface, of its atmosphere, it has a reflectivity of about 80%. And that is called the albedo, the proportion of solar radiation that is reflected off materials. Usually we're dealing with a planet here. So 80% of that radiation flux density that we calculated for Venus, that 2,600 watts per meter squared, 80% is being reflected back off into space, and only 20% is making it into Venus's atmosphere, which means that if we just did a little energy balance here, we would find that the effective temperature of Venus is 227 Kelvin. Now remember, Kelvin is measured using an absolute temperature scale, whereas 0 Kelvin is absolute zero, the temperature at which all molecules stop moving. So 227 Kelvin is actually pretty chilly because 273.15 Kelvin is actually 0 degrees Celsius, the temperature at which water freezes or starts to melt, however you want to look at it. So 227 Kelvin is equal to minus 46.2 degrees Celsius or minus 51.1 degrees Fahrenheit. So Venus would be frigid, right, if we were just looking at the surface properties of the planet and its reflectivity. Even though it's close to the sun, it's reflecting most of its energy back out into space, whereas Earth has an albedo of only around 30%, maybe like 26%, it varies. And so Earth would have an effective temperature of 255 Kelvin, which is equal to minus 18.2 degrees Celsius, which is about 0 degrees Celsius, which is a lot cooler than, of course, we have noticed that it is. We'd have frozen water at the surface, right, at 0 degrees Fahrenheit and minus 18.2 degrees Celsius. Since water freezes at 0 Celsius and 32 degrees Fahrenheit, it would be very, very uncomfortable and really challenging for life to exist. However, the observed temperature, so the temperature that we actually measure on these planets, is quite different than the effective temperature just based on the reflectivity or albedo of the planets and the solar radiation flux density hitting the top of the atmosphere. So let's take a look. The observed temperature on Venus is 460 degrees Celsius or 860 degrees Fahrenheit. So the effective temperature is about 500 degrees Celsius higher than the effective, meaning that the greenhouse effect on Venus is about 500 degrees Celsius. So the greenhouse effect, recall, is dependent on the composition of the planet's atmosphere and its proportion of greenhouse gases. Now looking at Earth's greenhouse effect, the observed temperature is about 15 degrees Celsius or 59 degrees Fahrenheit. So we have a greenhouse effect of about 40 degrees Celsius, or so 33 to 40. So the greenhouse gases help keep Earth at a much comfortable temperature of 59 degrees Fahrenheit is much more comfortable on average than 0 degrees Fahrenheit. Now, this is just showing how solar radiation comes in to the atmosphere of Venus versus that of Earth. So looking at these cross sections, Venus is on the left, Earth is on the right. The yellow arrows represent short wave solar radiation. So this is what is coming into the atmosphere. And remember, Venus has a really high albedo. So it has these reflective outer cloud layers where 80% of the incoming sunlight is reflected back into space. Whereas the 20% that gets through is absorbed by the surface of Venus, increasing the planet's temperature. And because the planet has a temperature that's greater than absolute zero, it's going to emit thermal radiation back off of its surface. And this is long wave infrared radiation. So the long wave infrared radiation interacts with the greenhouse gases in Venus's atmosphere. Keep in mind that Venus's atmosphere is about 96% carbon dioxide. So the carbon dioxide in Venus's atmosphere absorbs this long wave radiation emitted by Venus's surface, gets excited, emits it back down to Venus, and what has happened is we have created this runaway greenhouse effect where very little of this long wave radiation emitted by Venus's surface is able to escape back into space. Whereas on Earth, our atmosphere is much thinner than Venus's. Venus's atmosphere, or the Venusian atmosphere, is 90 times more dense than Earth's. We'd get crushed. It would be bad. It would be bad, not to mention that it's raining sulfuric acid on Venus. It's also making it probably not a great place to visit. But on Earth, we have a much thinner atmosphere, and our atmosphere is only about 0.04% carbon dioxide today, whereas Venus is 96% carbon dioxide. So we can look at the energy budget in a very similar way here. We have incoming shortwave radiation coming in, and in Earth's case, only about 30% is reflected back off clouds, whereas the 70% comes in, interacts with Earth's surface, warms it up, the planet emits long wave radiation in the infrared range of the electromagnetic spectrum, and it is absorbed by greenhouse gases in Earth's atmosphere, so primarily carbon dioxide and water vapor, which is then re-emitted back down. But because Earth has a much thinner atmosphere than Venus, much of the long-wave infrared radiation is able to escape back into space, only giving Earth a slight warming effect, not this runaway greenhouse warming effect that you see on Venus.